A question that's often asked is, will loading my magazines fully hurt the magazines? And there's a simple answer, and then there's the more complex answer. And I'm going to try to give you both of them. First, one simple answer. No, it will not hurt your magazines to leave them loaded fully. The general response is that it doesn't hurt to leave them fully loaded, but it's the loading and unloading, constant loading and unloading of a magazine that eventually wears out the spring. That's the short answer. And I'm going to give a few conditions there. That's the short answer if the magazine is designed properly and if the magazine is manufactured properly. So two conditions there. Now for the long answer about why that is, give you an example of a pin. And this is a kind of material property. You'll notice the pin is straight, and if you hold the ends of it and bend it, you can bend this pin so it deforms like it does, like it's doing right there. And then when you let go, it'll still go back to its original shape. Now, that deformation is called elastic deformation. Now you can, as you well know, I don't want to break my pen, but you can bend it such that it will stay bent permanently. And once you've made it so it will be deformed permanently, it becomes plastically deformed. And different materials have different properties like this. For example, the pen is able to bend, and we call it ductile because the pen can change shape before it actually breaks. On the other side of that, you think of something like ceramics, or chalk is a good example. Chalk, when you try to snap chalk in half in a similar fashion to that pen, what will happen is it won't deform much at all. It'll just snap, and that's what we call something that's brittle. Your magazine springs are made out of typically steel, and steel is a ductile metal. And let me show you marked with my NRA bookmark. When engineers design your magazines, they will look at graphs similar to this one, and this is a metal, doesn't specify what metal, it's kind of a generic curve. The bottom axis measures how much strain there is, and strain is that deformation. Typically strain is change in length divided by original length, if memory serves me correctly. And over here is the stress, and the stress is in terms of pounds per square inch, or metric terms, something like megapascals, or typically that's what's used. But you see how there's a straight line along there, and then it starts to curve right about there. This whole straight line area is called the elastic region. As long as stress does not rise above that point and strain doesn't go beyond that point, it's going to return to its original shape. If you go beyond that stress, then you're going to deform it permanently. So each metal has a different graph like this. You see the one to the side, it can get a little more complicated in that there are certain phenomena that we don't really study in basic engineering thus far, but I'm giving you the simple complicated version. There is a complicated version, and I'm sure there's a version beyond that that's much more complicated. But that's just a generic thing. When an engineer will actually design your magazine, he will go to a table kind of like this one, and they'll look up something like what steel alloys they're thinking about using, maybe 4140, which is a specific kind of alloy, and they'll decide whether or not it's heat treated, and in what kind of way it's cooled, and then they'll get numbers established by certain, what's the names of them? I can't remember the acronym, but there are foundations and generally accepted values for all the things like yield strength, tensile strength, percent elongation. And yield strength is the stress. Unfortunately, I lost my page. Yield strength is the stress where is the estimated stress at which the material will go from elastic to plastic. In other words, where it will deform permanently. Once you've applied that yield strength, it will stay deformed and will not. Possibly that could lead to failure depending on what your application is. But when the engineers make your magazine and when they select the metal to be used for your magazine spring, that's all stuff they look at. And there are very well established, like I showed previously, there are well established stress curves, stress strain curves that show when this will deform. Now your magazine spring, once it deforms, it might lead to failure. On this particular one, if it's designed properly, I should be able to bend this. I don't know if you can really see that well. You can see those two coils getting very close together. Let me try to bring this closer to the camera. Those two coils getting very close together. When you bend them that close together, they're touching right there. If an engineer designed this properly and it was manufactured properly using a material that actually corresponds to the numbers that the engineer used when designing it, or engineers I should say, if that's the case, then this never deforms enough to undergo enough stress to permanently deform your magazine spring. And just like I showed you with this example, if this can bend and come back to its original shape, that's the same property that's being utilized here. And that's that energy to push up once it's been deformed is what ends up loading your magazine. Is what keeps around at the top of the mag body at all times. Now separately, what I just showed you is that the magazine spring, if properly designed and properly manufactured, if it's fully compressed, it should not matter, because this is not something that should, again, if designed properly, if made properly, it shouldn't get into the plastic region ever. At any time inside the mag body, should it ever get into the plastic region. The only reason it could possibly do that is if, for example, my finger's out of the way so you can see the coils. If this coil were to pass this coil going in that direction, meaning when they got close together, this one actually went upwards and passed it, that's the only way they could plastically deform. And that can't happen inside the mag body because the mag body restricts its movement from side to side to try to pass each other. So they can't plastically deform in that way. However, there is such a thing as fatigue loading. And fatigue loading, I don't know if, surely everybody has broken a paper clip at some point in their life. But you'll notice that when you try to break a paper clip, even if you, I don't know how, this is a high quality paper clip, but if you move it all the way to the other side, I just bent that, folded it in half, it doesn't break. And I bring it all the way back, again, still doesn't break. Bring it all the way back, doesn't break. Back, 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 back. And eventually, you have to do that over and over and over until finally it breaks. And that's what you would call a fatigue loading. It was never enough stress to make it completely fracture, but because I repeated that over and over and over and over again, it finally fractured. and I will see you in part 2.